So, first of all, thanks for coming to our science-filled panel Thursday evening at MAGFest.
So panel. They usually give me this panel in the morning, which is a morning panel. Everyone's going to be passed out, but the people who are ready to think, morning people. Also, generally not drunk maybe a bit hungover in the morning. All right, well, it's time, so let's get this rolling. I am Donald Gregorich. I am an aerospace engineer.
I'm Josh Brule. I have played a lot of video games that have space in it.
Yeah, as have I, as have we all. So, and in fact, I first thought of this panel a few years ago. I was playing a lot of video games. What was that, 2016? Seemed like kind of a renaissance in gritty space games. We had Elite Dangerous, that's still around to this day. No Man's Sky, kind of but it's good now. So the developers have come out of hiding. I'm happy for them. 2016, Star Citizen was coming out any month. It was going to be awesome. Maybe it still will be. But as I said, I'm an aerospace engineer, and I can't help but think about certain things when I'm playing video games. Like FTL, you got to manage all your subsystems. It's got life support weapons. It has a subsystem for the doors. There's no system for the artificial gravity. You'd think that'd be pretty important, right? Everyone just kind of ignores artificial gravity. No big deal. Kind of a big deal. This is an indie game called House of the Dying Sun, which was pretty cool. And this one took the space fighters to the extreme because you have a turning radius and there's drag in space. I don't know what's slowing you down.
Space. Yeah. So what I realized pretty early on, Star Wars TIE Fighter. And it was Star Wars, the original movie, which kind of ruined everything because all of the everything's based on Star Wars combat, right? A New Hope, the ships swooping around and stuff. And Star Wars combat was based on World War I air combat. So when you're playing these space games, you're actually playing a World War I combat simulator without gravity and missiles. And of course, a game I love, but it goes kind of ridiculous with the space opera stuff, Mass Effect. And if you know Mass Effect, you might recognize the title for this panel. It's kind of one of my favorite moments in Mass Effect 2, which kind of contrasts a bit with the other stuff going on in Mass Effect. And here it is for your viewing pleasure. If I turn on my sound. All right, here we go.
This recruits is a 20-kilo ferrous slug. Feel the weight. Every 5 seconds, the main gun of an Everest-class dreadnought accelerates 1 to 1.3% of light speed. It impacts with the force of a 38-kiloton bomb. That is 3 times the yield of the city buster dropped on Hiroshima back on Earth. That means Sir Isaac Newton is the deadliest son of a bitch in space. Now, Serviceman Burnside, what is Newton's first law?
Sir, an object in motion stays in motion, sir.
No credit for partial answers, maggot.
Sir, unless acted on by an outside force, sir.
Damn straight! I dare to assume you ignorant jackasses know that space is empty. Once you fire this hunk of metal, it keeps going till it hits something. That can be a ship, or the planet behind that ship. It might go off into deep space and hit somebody else in 10,000 years. If you pull the trigger on this, you are ruining someone's day, somewhere and sometime. That is why you check your damn targets. That is why you wait for the computer to give you a damn firing solution. That is why, Serviceman Chung, we do not eyeball it. This is a weapon of mass destruction. You are not a cowboy shooting from the hip. Sir, yes, sir.
So is Newton really the deadliest son of a bitch in space?
That's a good question, Josh, and that's exactly what I want to find out in this panel. So, of course, we've got Newton, but there's a lot of other guys who are very important to the
let's say, like space physics and engineering. We've got Tsiolkovsky here, and Robert Goddard, and Einstein, of course. And we even got, I'm blanking here. Thank you, Werner von Braun. How could I forget him? So, of course, we'll start out with Newton here. I'd say Newton's pretty deadly. He's also definitely an SOB, if you know anything about his history. And of course, as we just heard, we heard about one of Newton's laws, but he came up with 3 of them. And this basically created classical physics as we know it. So of course, I've written them in more plain language here because it's easier to understand the actual what's going on here. So of course, number 1, object in motion remains in motion unless acted upon by an outside force. Number 2, acceleration is proportional to force and is in the same direction as the applied force. And we just write this as a simple equation. Force is mass times acceleration. And then number 3, when an object applies a force to a second object, the second object applies a simultaneous and equal force upon the first in the opposite direction. A lot of times we call this equal and opposite forces. But Newton came up with these laws, but he wasn't done here. See, somebody asked him to figure out how orbits worked, and Newton basically just said, okay, give me a few months, I have to invent calculus first. And then he comes back with the law of gravitation here. So we got a force, we have this constant, which is just a really small number, and then you take the mass of 2 objects. So usually the first one is something really big, like a planet or a star, and then you take the mass of a second object, something smaller. We're going to be using spaceships here. And then you find the distance between the things, and it'll let you calculate the gravitational force. Now, if you take this equation and you do all this stuff to it, then,
very clear.
Yeah, we'll just kind of, glaze over that. But what we can figure out is we can calculate a single acceleration for any object on the Earth. So, or the moon, which is what I've done at the bottom there. And so what this means, it's the famous hammer and a feather thought experiment, which was done as a real experiment by one of the Apollo astronauts. Hold on. Sorry, got to do my sound here. It makes this horrible noise every time I plug it in. I don't want to deafen you guys, so.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that?
How about that? Yeah. So, so that's an important thing here, is all the objects in a gravity field will move at the same acceleration. And when we're talking about accelerations, we can say, well, if something is accelerating down towards the Earth, conceptually, that's almost the same as if you were still and the planet was accelerating up towards you, and we can say, well, why does it have to be a planet? What if it's a spaceship, right? Because spaceships tend to accelerate. That's what they do. So I've got the Normandy here, because I was talking about Mass Effect earlier. And the thing with the Normandy is that all the decks are laid out like this. It's kind of like a modern airliner. And so if the Normandy is accelerating in this direction, that means you're going to go that direction.
Oh, okay. The codex in Mass Effect makes it very clear that they build gravity panels into the entire floor of a Normandy.
Gosh, who reads the codex?
A friend told me.
Okay. So, so there is a recent TV show where you do not need to read the codex. That's The Expanse. The Expanse is, yeah, go watch it. It's like the best thing not on television right now, because who watches television anymore? Anyways, Yeah, so in the Expanse, all the ships are built like towers, and they have the decks going this way. So when the ship accelerates like this, you get pushed into the deck in the same direction as gravity. And that's actually how they make artificial gravity in the universe of the Expanse. All right, so now we're going to talk about orbits. So, because we've got the basics of gravity here, and this is how gravity affects you when you're in orbit. And there's a quote here which I really like. It kind of sums up how to think about orbits conceptually. There is an art, or rather a knack, to flying. The knack lies in learning how to throw yourself at the ground and miss. Clearly, it is the second part, the missing, which prevents the difficulties. And that's from The Hitchhiker's Guide to the Galaxy. And while not literally true, because Douglas Adams proposed that in order to miss the ground, you just have to get really distracted right before you hit the ground. It doesn't really work. I've got a better method. So we got the Earth here. Imagine if we built a really, really tall tower, right? And then we're going to stand on top of that tower. And we got a baseball in our hand, or just any sort of object. So if I'm on top of this tower, I'm way out of the atmosphere, and I let go of this ball, what's going to happen with it? It's going to fall straight down, right? Gravity doesn't go away just because we've got it. It gets a little bit weaker, but it's still there, and it's still going to pull in the same direction. But if I throw this ball, you'll notice that it's fallen farther than before, because the Earth is the Earth is a sphere. It's curving away from the path of our ball. So if I can throw this ball hard enough, it will fall towards the Earth and miss. And because by the time it's over to the left side, gravity's pulling it to the right, so now it'll come around moving to the right, and now gravity's pulling up. It's all relative. But this is basically how an orbit works. We're falling towards the ground, and we're missing. And the direction of gravity is constantly changing, and so it's going to pull us around in a circle. I also want to do a little demonstration here, because it's late, and I want to make sure you're all paying attention. So let's all stand up. So what we're going to do here is I want everyone, I'm going to count down, 3, 2, 1, go. And when I say go, I want everyone to jump straight up in the air. And you don't have to jump too high, and make sure you don't run into the people next to you, all right? Ready? 3, 2, 1, go. All right, so the moment your feet left the ground, you were in 0G, all right? So congratulations, everyone. I got astronaut wings for everyone here. Yeah, sorry, that was a lie. I don't actually. But it's true that as soon as your feet left the ground, you were on the same sort of trajectory you would be in if you were in orbit. You just weren't going fast enough sideways. So instead of missing the Earth, you just ran right back into it. In this slide, we can see here, orbits are circles. Well, what Kepler figured out a long time ago is that orbits aren't actually, they're technically not circles. They can be circles, but orbits are actually ellipses. A circle is just a fancy type of ellipse, right? And in an ellipse, we have 2 foci, and then the 2 ends of the ellipse, which we call the periapsis. That's the one closer to the body you're orbiting, and the apoapsis, which is the top. Think like apex, top of a mountain, apoapsis. And what's going on here is if we're in a circular orbit and we speed up, then the apsis on the opposite side of our orbit is going to raise. And if we keep speeding up, it'll keep raising. And if we speed up fast enough, then we reach the escape velocity, and we'll just at some point, just go cruising off into space, and won't come back to our original planet. And we can use this property of orbits to get around. So say we raise our orbit here, and then our spaceship goes over to the other apse, and we raise our orbit by the same velocity. We circularize it, make the orbit into a circle. Now we're in a higher orbit, and we call this sort of maneuver a Hohmann transfer, and we got Walter Hohmann here, who is not one of our main guys, but he gets a special mention for coming up with this maneuver in his spare time. Like, apparently this was his hobby. And we can even use this to go between planets. So if we raise our orbit here, all the way to another planet, and then when we get to the other planet, we slow down. There we go. That's how we get around. Of course, the question now is, how do we change our velocity? Because as you remember, space is empty. So, oh, here comes Newton again. So we're going to use Newton's third law here, which is the equal and opposite forces. If we've got another baseball here, and we throw it, the equal and opposite force, that ball is going to put a force back on us. We're going to move. So all we have to do here is, if you can imagine, if we could constantly throw mass at really high velocity, we'd go somewhere. And this is all a rocket engine is doing. It's using a lot of energy to move mass really quickly. And we can use our F equals ma equation here to figure out the amount of acceleration we're going to get is based on the mass of the propellant we can spit out, how fast it's accelerating, and the mass of our own spaceship. And you might notice something here. The acceleration is based on the mass of our spaceship, which we are spitting out the back of a rocket. So our mass is constantly changing. So that's where Tsiolkovsky comes in, because he came up with the rocket equation. And it's pretty important. You can probably imagine from something called the rocket equation. And what it does is it basically tells us our total, how do I say this? Yeah, our total amount of go, right? How far we can go. It's not like our range, because rockets could have almost unlimited range if you're willing to wait long enough. It's how much we can change our orbit, because remember, to change orbits, we have to change our velocity. So we read this as delta V. And if you hear an engineer talk about delta V, you can think of that as how much gas you have. And then we've got this here. This is called specific impulse. It's in units of seconds, and that's Earth's gravity. These are pretty weird to have an equation like this. Don't worry about them. The important part is that if you multiply them together, that gives you the exhaust velocity, the velocity of all of those baseballs you're spitting out the back of your ship. This here's a natural log, and that's the mass ratio. So how much propellant are you carrying versus the mass of your ship? And so if we can plot here, we've got our mass ratio. So that's kind of like how much of our ship is filled with gas. And then down here, that's our overall delta V over our exhaust velocity. It's just to represent delta V. And the point here is, okay, if we want our rocket to go farther, we add more propellant. That raises our mass. We need to use more propellant to move that mass. That means we're probably going to have to add more propellant. You get diminishing returns. And sometimes we refer to this as the tyranny of the rocket equation, because it means if you want to go farther, it gets harder. And because of this, our rockets end up being mostly propellant. And so this is a Saturn V, and everything blue here is all propellant. That's all rocket fuel. So this giant thing, almost like, well, definitely the size of a building, just to move this little capsule. And of course, sci-fi doesn't really care about that. Like, where are the fuel tanks on the Millennium Falcon? So the simplest way of getting this propellant to move at a high velocity would be with a liquid fuel engine. So you probably know there's no air in space. So we need to bring oxygen with us in order to create a combustion with fuel. And it's a relatively simple conceptually. We're just going to take some really high-powered pumps and combine this fuel together, and we need a lot of fuel because we need a lot of power. And then the fuel and oxidizer will combust and expand, and then we can use that to expel the exhaust gases at the high velocity that we need. So let's take a look. Pretty much all of our rockets use this technology right now. And I kind of want to compare where we are with this technology with the kind of stuff we see in sci-fi. So I went and picked out a sci-fi spaceship here. And this guy looks to me kind of like the size of a fighter jet. So I want to see, all right, what if we took a fighter jet-sized spaceship and wanted to get it into orbit around the Earth with chemical propulsion? How would that go? So using the rocket equation here, I need to know how much delta V we need to get to, this is low Earth orbit. This is pretty much the orbit that the International Space Station is in. It's about 400 kilometers altitude, and it's a circular orbit. So we're going to need 9.4 kilometers per second of delta V. We need to move our spaceship from our reference point of 0 to moving at 9.4 kilometers per second. And the dry mass, that's without fuel, of the F-22 here, 19,700 kilograms. And then that specific impulse, which is kind of the fuel efficiency of our rocket engine, is about 450 seconds. And remember, we can multiply that against Earth gravity to get the exhaust velocity, all that stuff. So the important part here is we end up with this mass ratio of 8.4. That means that we need to carry 8.4 times the dry mass in fuel to get to orbit. So our spaceship will look kind of like this. Okay, there's a way to solve this, and it's with more power. And Einstein, came up with the physics that eventually gave us nuclear reactors. Pretty simple conceptually. We just take some propellant, run it through a nuclear reactor, add a lot of heat, it'll cause that expansion, and then boom, we'll get some really high velocity exhaust here, give us a lot of go. So that raises the ISP up to about 850 seconds, and the mass ratio for that is 3.1. So that's a lot better, about 3 times our mass instead of 8.
For safety reasons, of course, we never did this.
Funny story, we did. Yeah, so this was back after the moon race. NASA thought we would go on to Mars pretty soon after that, and they were working on these kinds of nuclear rocket engines. And they were pretty successful, actually. And the only thing limiting these engines is actually the temperature at which the fuel rods melt. Because if you want more power, you just make it hotter. And so at some point, everything's going to melt. So that's kind of a limit there, except actually it isn't, because somebody went and thought, hey, what if we just let the fuel melt? What if we had a liquid-cooled nuclear reactor? No. What if we had a gas-core nuclear reactor? We get the nuclear fuel so hot that it becomes a gas. And if that's still not hot enough, we could use fusion power. Of course, we haven't actually got fusion power to work on Earth. I mean, we can create fusion reactions, but we need to add more energy than what we get out of them. But there is a technology that we already have that's very cheap and will reliably give us a lot of energy. And you might not like it. They're nuclear bombs. Nuclear bombs are actually really cheap. And so some other crazy person went and said, hey, what if we built a spaceship powered by nuclear bombs? So you'll notice that big plate on the back of this spaceship. Yeah, that's a They call it the pusher. It's basically a big shield on shock absorbers. And then they said, hey, we can do better than just a nuclear bomb. We'll make a nuclear-shaped charge, which will direct all of the nuclear energy at that pusher plate. And then we just need to regularly drop these bombs and detonate them, and it will push our spacecraft. And this leads us into what has been called John's Law of Sci-Fi, which is that any interesting space drive is a weapon of mass destruction. It only matters how long you want to wait for maximum damage. And of course, interesting is equal to whatever keeps the readers from getting bored. So this is something that gets ignored quite a lot in science fiction. Any of these spaceships capable of scooting around the solar system are all weapons. And that, if you need to be more convinced, we've got Rick Robinson's first law of space combat here, which is an object impacting at 3 kilometers per second delivers kinetic energy equal to its mass in TNT. Because of course, thanks to Newton's laws, objects collide, they exert force on each other, and exerting force is a good way to break things. So the picture here, by the way, that's a small crack in a window, and that's only 7 millimeters across. However, NASA believes that this was caused, this is a window on the space station, by the way. They think this was caused by probably like a paint fleck or a metal fragment that was probably about a few thousandths of a millimeter. So that, moving at orbital velocity, cracked a window on the space station. So you can imagine something larger moving. So, little experiment here using that law. In orbit, you're moving at about 7.6 kilometers per second. So let's say that we've got stuff in the same orbit, but going opposite directions. So if one of these ships were to just drop something in the path of the other, when those collide, the impactor would collide with about 25 times its mass in TNT. That's how much power it would apply to the other vehicle. So, and I mean, this shouldn't be a surprise that things moving quickly cause damage because we already use guns a lot in warfare. And that's the concept of a gun. And I use this picture here. This is from Firefly, of course. This was a great moment where Jane has to fire his gun in space, so he puts it inside a spacesuit. And this is a funny case of a TV show overcompensating, because the thought process here is, well, guns rely on combustion, and in order to have combustion, you need oxygen. So you put the gun in a spacesuit, but gunpowder actually contains its own oxidizer. And we already know that guns work in space because the Russians did it. So there was a space station, Salyut 3, where the Soviets thought, hey, let's put a gun on our space station. And who knows what they were going to do with it. Supposedly it did fire. We don't have any details because the records were lost when the Soviet Union collapsed. But there was a gun fired in space at some point. At least one that we know about. All right, so guns. Probably the highest performance gun we have right now would be like a battleship gun. That moves at 762 meters per second. So that's pretty good. But this is space combat. We can do better. Railguns. Let's use a railgun. And the way a railgun works is actually really simple conceptually. So basically, if you have current moving through a magnetic field, it will create a force at right angles to the current in the field. So all you need to do is, let me get a pen here. Here's my laser pointer. So we've got the magnetic field. When you move current through a wire, it generates a magnetic field. So we don't even need to use permanent magnets or anything. It will generate magnetic field in these circles. And then our projectile is going to conduct the current across this way. So we've got current going this way, magnetic field going this way, creates a force that way. Awesome, right? real simple way to move a projectile. But the thing you have to consider is that there's current going this way. That current is subject to a magnetic field going that way, which generates forces going this way, which means that a railgun is a device which is constantly trying to disassemble itself. So that's the kind of thing DARPA is working on right now. But they think once they get it working, their railgun will move at about 2,500 meters per second. So pretty good increase there. And that's why they would be pretty great in space, since the ranges you would be covering are going to be huge. Now, we were just talking about like spaceships and engines and stuff, and so you might say, well, why don't we use one of those as a projectile? And that's basically what a missile is. It's a little spaceship or a little rocket. And of course, we got von Braun to thank for some of that, because he developed the V2 rocket in World War II. And now von Braun, of course, claimed that he was just doing it for the engineering and had no desire to actually help the Nazis. And when asked about the V2 and whether he thought it was a success, he said, it worked perfectly, except it landed on the wrong planet.
I aim for the stars, but sometimes I hit London.
Oof. So,
Too soon?
So, of course, missiles are, I mean, they're real simple. Space missiles would probably be about the same as what we're using on fighter jets today. These are some concepts from video games. And now you wouldn't need fins on them, of course, because there's no atmosphere. Now these look cool. I always kind of imagined space missiles would probably look pretty boring. These were sprint missiles, which were used in the Cold War for intercepting bombers. And they had really high acceleration. Something like 10 times the acceleration of gravity, 10 g. That's pretty crushing acceleration. So then, of course, it's like, okay, you could have a kinetic impactor missile, or you could put a payload on it, and well, let's just go right for the top. Forget conventional explosives. Let's talk about nuclear bombs. So, it's the unfortunate reality that space combat will probably use a lot of nukes because they're very effective. And again, space is mostly empty, so you don't really need to worry about hitting bystanders. Conceptually, nukes are really simple. Basically, if you take radioactive material and you get enough of it in a small enough package, it will go critical and cause your nuclear explosion. So the very first types of nuclear bombs, in the upper left there, we just have two halves of a critical radioactive component, in this case, uranium. And then when you want the bomb to detonate, you accelerate one towards the other really quickly, and when they meet, you get your explosion. Later, they figured out they could use explosive lenses. They actually figured out how to manipulate the shockwave from an explosion. And so they would take a whole but subcritical amount of plutonium in this case, and use the explosives to compress this ball from all directions at once until it became critical. And then, of course, later they developed the hydrogen bomb, which uses a nuke as its fuse. So pretty terrifying weapons there, but no, you can't doubt their effectiveness. But my favorite sci-fi weapon, which kind of got left out for a lot of sci-fi history, is the laser. Lasers were super cool for a while, and then everyone thought they were weird and nerdy, I guess. And so we just got a lot of guns for a while, but I think lasers are making a comeback. Lasers are, of course, light. And the reason why a flashlight won't damage anything is because the light is just coming out at all different wavelengths and in all different directions. So if we want that to cause any damage, what a laser will do is we get a coherent beam, so all the light is going in one direction and it's all the same wavelength. And then we can pump a lot of power into this and we can use it to burn things. So conceptually, lasers are actually pretty simple. You just need a lasing medium. Early lasers used like a ruby rod. And all you're going to do is you got these mirrors here. You apply light, and the light will kind of bounce around in this lasing medium, and the lasing medium is like a filter. It's going to filter out only the wavelength we want, and it will come out only in the direction we want. But of course, in science fiction, lasers are always kind of pointy, which is weird because real lasers are pretty much the opposite. Real lasers have huge lenses because it's light. They're like cameras, really. These are two lasers developed by the US military. So the one on the left, that's in the nose of a Boeing 747 jet. So you can just kind of imagine the size of that. They thought maybe we could use this to shoot down missiles, but it turns out that you'd have to have the plane in the air, like near where the missile was being launched from at the time it was launched, so kind of makes it pointless. But extremely cool concept.
Your tax dollars at work.
Yeah. And lasers are being actively used in the military right now on naval boats, and there are some ground-based lasers. They're mostly used, a big application right now is shooting down drones. In the Navy, they can also use them for attacking small boats. And a possible future use could also be shooting down missiles, and we would call this CWIS, which is a fun acronym, CIWS, Close-In Weapons System. And it's basically, well, right now, we already have CWIS platforms, which are bullets shooting down missiles. If you're familiar with the A-10 Warthog, that's the main gun from an A-10 Warthog, the GAU-8. Somebody decided, hey, why don't we mount it to a ship, put a radar on it, and then use it to shoot down stuff that's coming at the ship. But you can imagine a laser being used in this application as well. And lasers are very versatile. We got all different colors, which is great for your sci-fi space battles. But most lasers would probably be non-visible light, infrared light. And but
what if we had more power?
Yeah, what if we had more power, right? We got visible light lasers. I think we can make ultraviolet lasers. We can make infrared lasers. But what if we make lasers with like X-rays or gamma rays? The problem is getting a source for that sort of radiation. And we do actually have one. Nukes generate a lot of power, gamma rays, and X-rays. So hey, let's strap a nuke to a laser. Somebody went and figured out that if you built this, set off the nuke, you would get like one short, very powerful laser pulse before the whole thing disintegrates itself. And that could actually, well, it's called a nuclear bomb pumped laser. It could actually be an effective weapon. You wouldn't want to be anywhere near it, so you would probably put it on a missile, shoot it somewhere far away, and then have it shoot something else. So pretty creative application of these technologies. Now, of course, big problem with lasers, big problem with everything we've talked about here, is it all generates heat. And when we talk about heat, we got to talk about thermodynamics, and so we've got a new guy. This is Carnot. He's called the father of thermodynamics, and he only published one book, but it was pretty important because it got people thinking about using heat as work. So at the time, in Carnot's time, steam engines had just been invented, and they were really popular, but people didn't really understand why they worked. They knew we create steam, the steam expands, it creates work. But Carnot was the first one to think about a theoretical cycle and like what would some of the math be behind these thermodynamic cycles. And a funny anecdote at the time, they thought heat was an invisible fluid, and they called it caloric. So that's kind of the precursor to where we talk about calories now. So Carnot didn't come up with these, but his work eventually led, and there are a lot of different scientists and engineers involved in the development of thermodynamics. And now, to this, well, their work led us to create laws of thermodynamics, and here are two important ones. There are more than these. The first one is energy can't be created or destroyed. So this is good and bad. One is you can't destroy energy, so that means you can move it places and have it do work for you. And you think, well, all those things I was talking about is creating energy. Well, no, we're actually just transferring energy from one form to another. So most of the time, chemical energy, and then turning it into like light energy or heat energy or kinetic energy. The second law, the other one that's important to us, is the entropy of a closed system always increases. Okay, so what's entropy? Well, it's this very simple equation.
That's clear.
Yeah, clear as mud. You don't need to worry about that. It's kind of hard to explain, but entropy is roughly, it's the amount of disorder in a system, and just know that heat is disorganized energy. So when we talk about a closed system is one where we say no energy comes in or out. And the only true closed system in reality is the universe. So think about that. The entropy of the universe always increases. What it's basically saying is anytime you use heat to do work, you get waste. And so let's use our space station as the example here. Anything we do on the space station, because that's all work, is going to create waste heat. And so here's an infrared view of the space station, because all that waste heat has to go somewhere. It can't be destroyed. And we're in space. There's nothing in space. So how do we move that heat? There's only one way to do it, and it's radiation. On Earth, like if anyone's built a PC, this is the example I think of because I build PCs. We use conduction and convection a lot. So conduction is if you have a hot thing and you touch it to a cold thing, the heat will move from the hot thing to the cold thing. And then convection is we're doing that with air. You heat up the air, heat rises, so it will cause a convection current, and we can move heat with air that way. Well, we don't have heat in space, and we're not touching anything. So we have to use radiation. And so we pump heat into these radiators. They heat up. They glow in infrared. They start emitting infrared light. And that's how we're getting rid of heat. It's actually the emission of heat through infrared waves, which has some implications for your spaceships. It means they glow really brightly in infrared, which kind of makes it hard to hide from things. It also means that your spaceships are going to have radiators all over them, especially if they have really advanced engines on them, which generate a lot of waste heat. So all this comes together to say, what would realistic space combat look like, right? And ultimately, it is going to look like that. Okay, I guess that wasn't a very funny joke. So it's going to be at extreme distances from each other. Space is empty, and if we're looking at advanced technology like those railguns that go extremely fast, and lasers, which they move at the speed of light, that's really fast. Although the lasers will eventually diverge, and so their range is pretty limited. But then missiles as well could possibly, if you have a really advanced engine technology, missiles could be really deadly. So ships would probably go down in 1 or 2 hits. But there's a lot of things we can do. If it seems glum, just remember, if you are an aspiring writer or something, you want to create a sci-fi universe, there's a lot of different assumptions you can make. One big one is missiles versus lasers. So I mentioned CWIS before, being able to shoot down incoming missiles. So some people say, well, future space combat would be dominated by missiles because they're just so effective. You could shoot hundreds of missiles and people can't dodge them, and the missiles will have stupendous range and be filled with nukes and blow everything up. Or you could say, well, maybe lasers will be really good. I'll just shoot down all the missiles with lasers, and so if you want to do any damage, you got to get in close. You can't rely on your missiles. So there's also the availability of power. What kind of reactors are going to be available in this sci-fi universe? Are they going to have fusion reactors on everything and be able to run tons of lasers or other exotic weapons? And then the maneuvering capability. How advanced are the engines? How fast can ships move around? In a fight, are your ships going to be dodging things all of the time, or are ships going to have to enter these orbits and not, just go on these predictable trajectories for a long time? And then, of course, what most of these things come down to is, do you want to be 100% realistic, or do you want to have a fun story? And sometimes we have to make some sacrifices for realism. But I don't think that that you always need to sacrifice everything. And that's partly why I do this panel, because, of course, I'm an engineer, and I would love to read stories which are a bit realistic. So, wrap this up. I have to give special thanks to Winchell Chung. If you were listening carefully, in that Mass Effect clip at the beginning, the officer there mentions Serviceman Chung. That is a reference to this guy. He runs a website called Atomic Rockets. There's the URL there. If you just Google Atomic Rockets, you'll find it, and it is a treasure trove of all the kinds of stuff I was just talking about. It's basically written as a how-to write realistic sci-fi guide. I think it's really fun to look at, even if you're not a writer. Very cool website. Has recommendations for TV and books and video games that are somewhat realistic. And that is all I have for you today. Thanks very much for coming. We do have plenty of time for Q&A. So, just going to put some rules here. Make sure it's a question. That means it ends in a question mark. Keep it to the topic, sci-fi space combat. Try to make it brief. Don't want to hear long essays. And please don't promote yourself. So, we have a mic up front. I don't know if it works, but if you want to ask questions, go head up to that mic. Even if it doesn't work, it'll be easier to hear you. Yeah.
Using real science, how would you explain shields?
Shields. Oh, that's a good one. I thought I wouldn't have time to talk about shields, but I guess I do have a bit of time. Yeah. So most of the time, shields are presented as energy shields, some invisible form of energy. Yeah, I see a guy waving his hands here. That's pretty much, if you want a Star Wars type energy shield, I don't know. There's not really any technology that we know of which does all of the things that energy shields do. Let's see, we've got electromagnetic fields, so that would be more useful for protecting from radiation. Maybe it could protect you from some of the radiation from a nuclear bomb, but not really. I have seen concepts for a sort of hybrid physical shield, if you could create a nanotube mesh, extend that out from your ship in kind of a bubble, and then you could use electromagnetic fields to hold it in place. So that's a pretty exotic idea, and the mesh, it probably wouldn't block projectiles completely, but it would help absorb the energy from lasers. It might bleed energy off of projectiles. Now, one thing you definitely can use is armor. And so you could have armor to protect against lasers, which would be ablatives, probably. That means lasers coming in, high energy. Your ablative material is designed to burn in a controlled way. So instead of that energy going into your spaceship, the energy just burns off a little bit of the shield and it's released as a gas harmlessly into space. And then, of course, protection against projectiles, kinetic armor, which we have lots of designs for already on modern battle tanks and such. So there are lots of different ways of building armor like that. And then, of course, like the active defense systems, so using lasers or guns in a sort of point defense capacity. You could do various things with that. Cool. Do we have any other questions?
Okay, so real quick, you guys discussed a lot of the common sort of weapon types for science fiction. Almost said science fantasy.
Yeah.
That's really what this is.
Sure.
Like kinetic weapons, explosives, lasers.
Yeah.
Really common trope that I noticed was not addressed was like plasma.
Oh, okay. Let's talk about plasma. Yeah. The problem here is plasma is kind of like shields in that you squint at it and it just kind of doesn't make sense. So if a plasma, and in another presentation I did have like a slide on plasma, and the picture I used was the sun, because the sun is plasma. And a plasma is just if you really superheat a gas. So you know, it's another state of matter. It's really behaves just like really hot gas. And so if we talk about a plasma weapon, it's like we're directing a plasma at something, and then presumably the high energy plasma will burn it. The thing is, okay, think about trying, back it up. Imagine you just have a tank of some kind of gas and you are trying to shoot it at something. You can't really do that. Gas just kind of goes out into space and expands off, because gas always tries to fill the container it's in. So we don't really know how you could direct a plasma in a way that would be a useful weapon. Now, if we want to continue on the more exotic weapons, the one idea that I do like, which doesn't show up as often as it should probably, is a particle accelerator. So a few years ago, you might remember the Large Hadron Collider was a big deal. That's a particle accelerator. And you're using electromagnetic fields to take extremely small particles and just shoot them really fast. And so if you think about the guns we were talking about, if you have something that has mass and you move it quickly, you can do damage with it. So you could create a particle accelerator to use as a weapon, and it would be an interesting in between a laser and a railgun, a high-speed projectile weapon. It would not have the range of a laser, but it would be much faster than even the most powerful railguns. So, particle accelerators. Cool idea. All right. Are there any questions? Go ahead. Josh, you have anything?
I mean, what about antimatter?
Oh yeah, antimatter. Jeez, giving me all these ideas for slides I wish I had earlier. So, antimatter is pretty simple. You take matter, you take antimatter, you put them together, they annihilate and release a lot of energy. And I mean, I don't know much about quantum physics, so I don't want to get into try to explain what antimatter is, because honestly I don't really know. So there's a big problem with antimatter, and it's how I mentioned that it annihilates normal matter. So the big question here is, how do you store it? And that's probably something you could say, well, if my sci-fi is advanced enough, they've come up with some kind of containment system. And maybe it would use magnetic fields to hold the antimatter. There's also creating the antimatter, And I mentioned the LHC. The LHC creates tiny, tiny amounts of antimatter, too small to be useful, but maybe your future sci-fi civilization has perfected that process. So antimatter, it's a very, very advanced sort of technology, but if you were going to write a sci-fi universe that was that advanced, then antimatter would be a pretty good option. Now, a big problem with that, and also with the, this kind of goes back to like the gas core nuclear reactors, they are outputting so much energy that it's difficult to harvest. It's how do you capture that energy without destroying your own engine or your whole spaceship? So, example with the gas core nuclear engine, they thought the way to contain gaseous reacting nuclear fuel, you could, if you created a perfect crystalline quartz light bulb, essentially, then the quartz is transparent enough where the energy flowing through it wouldn't destroy it. However, if a mosquito landed on your quartz light bulb and pooped on it, you had this little tiny, tiny speck on your quartz light bulb, and you fire up that reactor, that tiny imperfection will absorb enough energy to just completely destroy that nuclear light bulb. So you'd have to have some pretty advanced technology to keep that surface pristine and free of imperfections. So that's just an idea of the energy levels you're dealing with. And antimatter would be even more extreme than that. All right, so we're pretty much out of time. Thanks very much, everyone, for coming. I know it's late, but I love doing these panels, and I'm glad you were here to see it. Have a great MAGFest. Oh, I just want to plug, Josh and I are doing another panel. When is that?
Saturday at 11 p.m. We're talking about weapons to surpass Metal Gear, which are the dumbest things that a military has ever tried to do in real life.
Yeah, that one should be fun. It'll be a good time. Come to that.
Like I said, they normally schedule us for like the morning crowd, and then it was kind of weird to put our science-heavy panel at like Thursday evening. But
yeah,
thank you all for coming anyway, because we did not know how many people to expect.